discussing the receptor theories and their importance in medicinal chemistry. Receptors are specialized proteins or micromolecular complexes typically located on cell membrane or within cells that binds to ligands such as drug, hormones, or neurotransmitters, initiating a cascade of physiological response. So these receptor theories form the cornerstone of modern pharmacology and medicinal chemistry, providing a framework for understanding how drugs interact with specific biological targets to produce therapeutic effects. So on the types of receptor. In medicinal chemistry, receptors are critical biological targets for this drug design and development, as they mediate the physiological effects of drug by recognizing and binding specific ligands such as neurotransmitters, hormones, or synthetic molecules. Receptors are typically protein or protein complexes that upon ligand binding initiate a cellular response such as signal transduction, gene expression, or enzymatic activities. Understanding these types of receptors is essential for designing drugs with high specificity and efficacy. This comprehensively explores the major types of receptors relevant to medicinal chemistry, their structural and functional characteristics, and their significance in drug development. So more, we have the G protein coupled receptor. The G protein coupled receptors are one of the largest and most pharmacologically significant receptor families, accounting for approximately 30 to 50% of marketed drugs. When a ligand binds to this GPCR, it activates an associated G protein by exchanging GDP, which is guanine diphosphate, the inactive form of the guanine nucleotide, for GTP, which is the guanine triphosphate, the active form. The activated G protein can then interact with other proteins or enzymes in the cell, leading to a variety of intracellular responses. GPCRs are involved in many physiological processes, including vision, taste, and the immune response. GPCRs are critical for vision by detecting light, for taste by detecting sweet and bitter taste, for immune response by mediating chemotaxis, inflammation, and immune cell activation. They achieve this function through a complex interplay of receptor activation, G protein signaling, and downstream cellular response. So the ion channel receptor. The ion channel receptors are membrane proteins that form pores to allow the selective passage of ions across the cell membrane, regulating membrane potentials and cellular excitability. They are classified into ligand-gated ion channels and the voltage-gated ion channels, both of which are critical drug targets. The ligand-gated ion channels, they open or close in response to ligand binding. The nicotinic acetylcholine receptor and the GABA A receptors are prominent examples. This receptor consists of multiple subunits. The pentameric structure in nicotinic acetylcholine receptor. They form an ion conducting pore. Drug targeting these ligand-gated ion channels include the benzodiazepines, e.g. the diazepam, which enhance GABA A receptor activity to treat anxiety and local anesthetics. And local anesthetics, e.g. the lidocaine, which blocks sodium channel. The voltage-gated ion channels respond to changes in membrane potential. The voltage-gated sodium and calcium channels are critical for neuronal and cardiac excitability. Anti-epileptic drugs, e.g. the lamotrigine, and antiarrhythmic drugs, the amiodarone, target the voltage-gated ion channels to modulate ion flow and stabilize membrane potentials. The drug design constitution. The ion channel modulators must achieve high selectivity to avoid off-target effects.
Ion.
Mm-hmm.
It sounds like iron. You don't
Okay.
understand.
Ion channel modulators must achieve high selectivity to avoid off-target effects, as these channels are widely expressed across tissues. Computational modeling and electrophysiology are used to design drugs with precise using profiles. So number 3, we have the nuclear receptors. The nuclear receptors are intracellular transcription factors that regulate gene expression in response to lipophilic ligands such as steroids, thyroid hormones, and retinoids. These receptors are located within the cell, typically in the cytoplasm or nucleus. They bind to small hydrophobic ligands, like the lipophilic ligands, such as steroid hormones, the cortisol, estrogen, that can easily cross the cell membrane. So once they bind to this ligand receptor, they translocate to the nucleus and bind to a specific DNA sequence and regulate gene expression. Example and therapeutic application. The key nuclear receptor, including glucocorticoid receptor, targeted by corticosteroids like prednisolone for inflammation. The estrogen receptor, targeted by tamoxifen for breast cancer. And the perisystem proliferator activated receptor, targeted by tazolidenodions for diabetes. Number 4, we have the enzyme linked receptor. The enzyme linked receptor. These receptors have extracellular ligand binding domain and intracellular domain that has enzymatic activity, often functioning as a kinase. So once a ligand binds to this receptor, it activates intracellular enzymatic activities, leading to the phosphorylation of specific target protein. This phosphorylation can trigger a cascade of signaling events that result in various cellular responses, such as cell growth and differentiation. Examples include receptor tyrosine kinase, which are critical in regulating cell division and survival. The therapeutic application. The tyrosine kinase inhibitors, such as imatinib for chronic myeloid leukemia and elontinib for lung cancer, block ATP binding to kinase domain, inhibiting aberrant signaling. The monoclonal antibodies like the trastuzumab target the extracellular domain to prevent ligand binding. So the other types of receptors, we have the adhesion G protein coupled receptor. We have toll-like receptor, which is located on immune cell surface, recognize pathogen associated molecular pattern and are targeted for immunomodulatory drugs, e.g. imiquimod for viral infection. We also have the intracellular receptors, non-nuclear. Some receptors like sigma receptors are intracellular and modulate pain and neuropsychiatric disorder through their mechanism, though their mechanism are less understood. So significance in medicinal chemistry. Receptors are central to drug discovery due to their role in mediating physiological and pathological processes. Medicinal chemists use techniques like high throughput screening, molecular docking, and fragment-based drug design to develop ligands with optimal affinity, selectivity, and pharmacokinetic property. Challenges include minimizing off-target effects, overcoming receptor desensitization, and addressing resistance mechanisms, particularly in cancer therapies targeting the tyrosine kinase. So, advanced instructional biology, computational chemistry, and artificial intelligence are accelerating the design of receptor-targeted drugs. So, we are moved to the major receptor theories now. In medicinal chemistry, receptor theories provide foundational framework for understanding how drugs interact with receptor to elicit pharmacological effects. These theories provide a frame for understanding how drugs interact with receptors to produce their effects. Number one, we have the occupancy theory. The occupancy theory was proposed by Clark in the 1930s. It's one of the earliest receptor theories and posits that pharmacological effect of a drug is directly proportional to the number of receptors occupied by the drug. According to this theory, a drug efficacy depends on its ability to bind to the receptor, and the maximum effect is achieved when all available receptors are occupied. The principle is that the drug receptor complex formation follow the law of mass action when the binding affinity to the social constant determines the strength of interaction. So the basic idea of this occupancy theory is that the intensity of drug effect is directly proportional to the number of receptors occupied by the drug. So more receptor occupied, the stronger the effect. And the key point is that occupancy theory assumes that a drug needs to bind to a receptor to cause an effect, and it doesn't account for the fact that some drugs can produce a maximal effect without occupying all receptors. We have the rate theory as well. The rate theory was proposed by Patton in 1961. The rate theory suggests that pharmacological effect of a drug is proportional to the rate of drug receptor. Is proportional to the rate of drug receptor association and dissociation rather than the absolute number of receptor occupied, like the occupancy theory. So this theory emphasizes the kinetic of ligand receptor interaction. The frequency of receptor activation events, that is the rate of drug binding and unbinding, determines the magnitude of the response. Agonists have a high association and dissociation rate, leading to frequent receptor activation, while antagonists bind more stably, reducing activation events. The theory accounts for the dynamic nature of receptor interaction, particularly in systems where rapid signaling is critical, such as a ion channel. So the basic idea of this rate theory is that a drug is related to the rate at which the drug binds to and dissociates from the receptor. And the key point is that it's focused on the dynamic interaction between the drug and the receptor. And it suggests that the speed of binding and unbinding is more important than just the number of receptors it occupies. Number 3, we have the induced theory. Induced fit theory. The induced fit theory originally proposed by Kochland for enzyme substrate interaction and later adapted for receptor, posits that ligand binding induces a conformational changes in the receptor, stabilizing an active state that elicits a response. Unlike the lock and key model, which assumes a rigid receptor, the induced fit model emphasizes receptor flexibility. The principle is that the receptor exists in a dynamic equilibrium of conformational states, and ligand binding shifts this equilibrium towards an active conformation. The degree of conformational change correlates with the ligand efficacy, e.g., agonists induce significant change while antagonists stabilize inactive states. This theory accounts for the structural adaptability of receptors, particularly G protein coupled receptors and receptor tyrosine kinase and receptor tyrosine kinase. So the application in medicinal chemistry is that the induced fit theory underpins structure-based drug design, where high resolution techniques like X-ray crystallography reduce ligand-induced receptor conformation. For example, the crystal structure of beta-2 adrenergic receptor bound to agonists has guided the design of selective bronchodilators. It is critical for developing allosteric modulator which bind to sites distinct from the orthosteric site. and stabilize specific receptor conformation. The allosteric theory now. The allosteric theory, formalized by Monod, Wyman, and Chanchus in the year 1960s, and extended to receptors, describes how ligand binding to allosteric, that is the non-active site, modulates receptor activities without directly competing with the orthosteric ligand. The principle: receptor exists in equilibrium between active and inactive states, and allosteric ligands shift this equilibrium by binding to distinct sites. Positive allosteric modulators enhance the receptor response to the orthosteric ligand, while negative allosteric modulation reduces it. Allosteric modulators can increase selectivity and reduce off-target effects, as allosteric sites are less conserved than the orthosteric sites. The application is that allosteric modulators are widely employed for GPCRs and the ion channels. For example, the benzodiazepines act as the positive allosteric modulators of the GABA A receptor, enhancing its inhibitory effect for anxiety treatment. Allosteric inhibitor of the tyrosine kinase, such as allosteric EGFR inhibitors, have been developed to overcome resistance to traditional orthosteric inhibitor in cancer therapy. Computational modeling and fragment-based drug design are used to identify novel allosteric sites. The two-state model. Another major receptor theory now. The two-state model proposes that receptors exist in equilibrium between two conformational states. An active state have an inactive state and an active state. The ligand stabilizes one of these states, shifting the equilibrium to modulate receptor activity. So the basic idea of this is that the receptor can exist in two states. They exist in an inactive state and an active state. Drug can shift the equilibrium between these states. An agonist favors the active state, leading to a response. Antagonists may bind to the receptor but shift the equilibrium towards the active state. The significance in medicinal chemistry. Receptor theories guide the rational drug design by providing mechanistic insights into ligand-receptor interaction. The occupancy and rate theories inform traditional pharmacodynamic models, while the induced fit, allosteric, and two-state models support advanced drug discovery strategies such as allosteric modulation and biased agonism. These theories are integrated with modern techniques like molecular dynamics, stimulation, high throughput screening, and cryo-electron microscopy to optimize drug potency, selectivity, and safety. Challenges include accounting for receptor heterogeneity, signaling complexity, and resistance mechanism, particularly in chronic diseases like cancer. So the quantitative aspect of receptor binding. The quantitative aspect of receptor binding deals with the measurable and numerical aspects of how a ligand interacts with a receptor. It involves determining the affinity of the ligand to the receptor, the number of receptors present, and how these factors relate to the biological response. So number one, we have the binding affinity and dissociation constant. The binding affinity quantifies the strength of the interaction between a ligand and a receptor. A cornerstone of receptor pharmacology is typically expressed through this dissociation constant, which is derived from the law of mass action. The principle is that the interaction between a ligand and a receptor to form a ligand receptor is described by the reversible reaction. The reversible reaction, which is L plus R. Where L is the free ligand concentration, R is the free receptor concentration, and the LR is the concentration of the ligand receptor complex.
I thought you said it's a reversible reaction. Is that
Sorry. So LR is the concentration of the ligand receptor complex. For example, quantitative methods. Binding affinities are measured experimentally using techniques like radioligands, building like radioligands, binding assays, surface plasmon resonance, or isothermal titration calorimetry. This method determines the application in medicinal chemistry. High affinity ligands are prioritized in drug design to ensure effective receptor engagement at low dose, minimizing off-target effects. Number 2, we have the dose-response relationship and the EC50. The dose-response relationship quantifies the functional outcome of receptor binding by measuring the biological response as a function of ligand concentration. The EC50, which is the effective concentration for 50% of the maximal response, is a key parameter in this relationship. The dose response is described by the U equation. Where E is the effect, E mass is the maximal effect, the L is the ligand concentration, the L is the ligand concentration. The quantitative method. Those response experiments are conducted using functional assays to measure. These assays are often high throughput to screen large compound libraries. Then we have the receptor occupancy and the occupancy theory. The receptor occupancy is calculated as the occupancy theory predicts that the maximum response occurs at full receptor occupancy. The binding kinetics. The binding kinetics is a quantitative aspect of receptor. The binding kinetics is a quantitative aspect of receptor binding that focuses on the rate at which a drug interacts with a receptor, how quickly a drug binds to a receptor, and how quickly it dissociates from the receptor. Efficacy and intrinsic activity. The efficacy quantifies a ligand ability to activate a receptor or form binding. Distinguishing agonists, partial agonists, antagonists, and reverse agonists. This intrinsic efficacy reflects the capacity of the ligand receptor complex. to produce a response. The importance of these receptors theories in medicinal chemistry: they help guide rational drug design, they enhance drug selectivity and safety, they optimize pharmacological efficacy, they help address drug resistance, supporting personalized medicine. We have some case studies. Beta-2 adrenergic receptor agonist for asthma. The beta-2 adrenergic receptor, a G-protein coupled receptor, is a key target for asthma and chronic obstructive pulmonary disease treatment. Agonists like salbutamol and formoterol activate the receptor to induce bronchodilator. So the application of this receptor theory is now the occupancy theory. This theory guides the design of beta-2 adrenergic agonists by correlating receptor occupancy with bronchodilation. Salbutamol, which is a short-acting beta-2 agonist, was developed to achieve high receptor occupancy at low dose, ensuring rapid onset of action. The induced fit theory. Structural studies reveal that the agonist binding induces a conformational change in the beta-2 adrenergic receptor, stabilizing an active state that couples G-protein to increase the cyclic AMP. High resolution X-ray crystallography of the receptor bonds to agonists like salbutamol provided insights into ligand-induced conformational change, enabling the structure-based design of selective agonists. So in conclusion, receptor theories, occupancy theory, rate theory, induced fit, allosteric, and so provide a robust theoretical framework for understanding drug-receptor interaction, shaping the field of medicinal chemistry. These theories explain how ligand binds to receptor, modulate their activities, and produce therapeutic effects, guiding the rational design of drugs with optimized potency, selectivity, and safety. From the quantitative models of the occupancy theory to the dynamic conformational insight of the induced fit and allosteric theories, these concepts have revolutionized drug discovery, enabling the development of targeted therapies for complex diseases. In medicinal chemistry, receptor theories remain indispensable for translating molecular insights into clinically effective pharmaceuticals, driving advancement in personalized medicine and therapeutic innovation. Thank you.
All right. Thank you very much for the presentation. Any question? Any question? No question. Now, stay on this reference, please. There's something I've noticed. If you are carrying out research, and most times, if you copy a document, maybe if you see a document, most times, if you copy it and it has mathematical formulas, once you copy it and paste, everything, it will give you something else. And that is what you are passing through now. And this formula in the board, look at the beautiful formula you render useless on the board because of the copying. Before you copy, I advise, look at it. If you reach there, you may just you can screenshot it and keep aside. Now, when you are now after copying whatever you want to copy, and when you are now working on the, of course, you don't copy the document verbatim. Hope you know. But let's assume if you screenshot it and keep, as you are writing your work now, you now use your hand to type it. If it is formula, you know how to play around your MS Word, how to put over, how to put square. You know how to do that one. You now use it. You type it yourself. If not, if you copy it and paste like that, this thing will appear. Shift. See where is it? E is equal to E maximum dot. What is dot? What is dot? Is the point they put there. That arrow You see that L plus R, you see left arrow. He's trying to describe what happens. But he cannot kill himself. So by that you use that to do it. That thing you see N, that thing L bracket, that thing that looks like, that thing is L raised to power N. That is what it is. Is that clear? This EC50 is EC50 raised power is E raised power N. As in EC50. Of course, you know what EC50 is now. What is EC50?
Effective concentration for 50%.
Good, yeah. Raised power N. That is the meaning. Is that clear? Please, next time as you're working, once you see a formula, if you copy it, it will just scatter and start giving you what you don't even know. You can't even understand it. Is that clear? So you can easily do a screenshot it, keep aside, then type it yourself in your work. That also affected you in your own work. She's laughing. All right. Thank you very much. Thank you very much. God bless you.